In this video, we are going to talk about improper integrals that have an infinite discontinuity. So I call these improper integrals of type 2. So let's start with the definition. If I have a function that's continuous on this interval from a to b, and what this notation means, it's continuous everywhere on the interval except at this right endpoint at b. So let's draw a picture of what this might look like. So I'll draw my axes. Let's draw some axes, and then I'll put my interval from a to b. And I want my function to be continuous everywhere on the interval except at that right endpoint. So I might have a vertical asymptote at b, and then maybe my function does something like this. So it starts here at a, and then it kind of snuggles up next to this vertical asymptote. And I'm interested in finding the area under that function's graph on this interval, so on that interval from a to b. So I'm interested in finding this area. And to do that, we are going to need to introduce a limit when we evaluate this integral, just like we've seen before. So the thing that's making this integral improper is the b here, because the b is where this function is undefined. Well, it's discontinuous. So what I'm going to do is replace that b with a variable. So I'll just call that t. And now I'm going to need to take a limit, take the limit as t approaches b, but from the left, because I just care about what's happening in this graph as my value of t gets very close to b, but from the left side. Okay, and as long as this limit exists, that's going to be the value of this integral. Okay, so I can give a similar definition if my function's discontinuous everywhere, if it's continuous everywhere except at that left endpoint a. So let's draw a picture of this. So I'll draw some axes, and then I'll have my interval from a to b. And now I'm going to put a vertical asymptote at that left endpoint at a. Let's go to draw mode. So vertical asymptote at a, and then maybe my graph looks something like, maybe there's a point at b, and then it goes down to the vertical asymptote. And now, when I evaluate this integral, I need to replace that lower limit, the a, because that's where it's discontinuous, with a variable like t. And then I'll take a limit as t approaches a from the right. Because on this interval, I just care about what's happening as I get very, very close to a, but from the right-hand side. Okay. All right. And then the final way I could have some type of infinite discontinuity like this is, well, what if my function's discontinuous somewhere in the middle at some number c that's between a and b? So let's draw a picture. So again, I'll draw some axes, and then I'll draw my interval from a to b, and I'm going to put some number c in between these two where the function is going to be discontinuous. So let's put a vertical asymptote there. And maybe my graph does something like, maybe there's a point here at a, and then it goes up to that vertical asymptote. And then maybe there's some point over here when x is b. And then maybe the function kind of goes down first. Maybe it kind of goes down first, and then it changes direction, and then it goes towards that vertical asymptote. So if something like that happens, then I have to split up my integral into two pieces. So I'll have to do one integral that starts at a and then goes up until that discontinuity at c, and then pick up my next integral and have it start at c and go up until b. So when there is a discontinuity somewhere in the middle, I'm going to have to split it up into pieces like this, where both of these are now situations like these first two, where it's either discontinuous at the right endpoint or the left endpoint. So if both of these integrals end up converging, meaning if they're both finite, then I just add them up, and that's going to be the value of this initial integral. Okay, so let's do an example. Let's say I want to evaluate this integral from pi over 3 to pi over 2 of this function. So I first want to have you pause the video for about 30 seconds to see if you can identify, well, what's making this improper? Like, where is this function discontinuous? So give it a quick pause for about 30 seconds. So pause it in 3, 2, 1, pause it. Okay, so hopefully you did that. Hopefully you paused it to think about where this is discontinuous. And the issue is at pi over 2. If you plug pi over 2 in, you get 0 in the denominator, and that's going to make this discontinuous there. So when I evaluate this integral, I'm going to have to replace that pi over 2 with a variable. I'm going to call it t, and then everything else stays as it is. So the pi over 3 down there, and then I got my function. So I'm just writing my function one more time, and that square root on the denominator. And then I'm going to have to take a limit. So, what is t approaching here? It's going to be approaching pi over 2, but is it from the left side or is it from the right side? So, I might be able to tell already, but if I wasn't sure, I could make a little number line for myself. And then I'm going to plot these two values. So pi over 3 is smaller than pi over 2. So I will plot those on my number line. And the value I care about is this pi over 2. So if I get very close to pi over 2 and I'm staying within this interval, well, I have to be approaching pi over 2 from this left side. I can't be approaching from the right side because then I'm outside of the interval, and we don't care about being outside the interval. So let us fill that in the limit. So I'm approaching pi over 2 from the left. So I'll put a little minus sign there to indicate that. Okay, so now I got my integral, and I got to evaluate this. So we can handle this with a u sub. So let's do a u sub, and I'm going to let u be the thing that's under the square root. So cosine x. And if we do that, then du, my derivative, is negative sine x dx. Because I have limits of integration, let's convert them, because right now they're in terms of x, but let's change them to be in terms of u. So right now my limits of integration are, there's x equals pi over 3 and x equals t. So let's plug these into the u sub. So if I plug in pi over 3, we'll get u equals cosine of pi over 3. That's 1/2. And then if I plug t into that, I get u equals cosine of t. Okay, so now I know what my limits of integration are in terms of u. So let us plug these in. So I'm getting this limit as t approaches pi over 2 from the left, where that lower limit has now become a 1/2. The upper one has become cosine of t. And then in my function, so I noticed that on my numerator, I have sine of x dx. And that's really close to what du equals. In fact, I can make that perfectly match up if I just move this negative sign to the other side. If I do that, I get negative du equals sine x dx. Okay, so let me highlight that. So negative du is sine x dx. So in the numerator of my integral, I have negative du, and the denominator becomes the fourth root of u. All right, so now we got to evaluate this integral. So I can simplify this function because I have that negative, and then moving up the root to the top and writing as exponent, I get u to the negative 1/4. And now I can do my antiderivative. This is just my reverse power rule. So I got this limit as t approaches pi over 2 from the left. And I got that negative in front. If I add 1 to the exponent, I get u to the 3/4. And then I would divide by 3/4, but that's the same thing as multiplying by 4/3. So I got this. Let's put my vertical line. Now I got to plug in that 1/2 and that cosine of t. All right, so if I plug them in, I get this limit as t approaches pi over 2 from the left. And I plug in, let's see, I'm going to plug in the cosine t. I'll get minus 4/3, big old parentheses, cosine of t to the 3/4 power. And then minus what I get if I plug in 1/2. So it's minus, I'll put a parentheses. And if I plug in, I get minus 4/3 times 1/2 to the 3/4 power, and then close that parentheses. Okay, so I've plugged in. Maybe I'll put a big old bracket around this whole thing because I'm taking the limit of this whole function. Well, the only part of this that has a t is this cosine t. Typically, the first thing that I do with a limit is I just try plugging this number, pi over 2 in. But I know cosine of pi over 2. That's just 0. So when I plug it in, this part just becomes 0. So what that leaves me with is that first part just goes away. It's just 0. And then I got a double negative, which becomes a positive. 4/3 times 1/2 to the 3/4 power. And we got it. So that is our answer. Okay, so we just did our first example of an improper integral that has an infinite discontinuity somewhere in the interval. So in the next video, we will talk about a common error involving improper integrals.